Hi everyone, welcome to my SPED Talk. I'm going to be doing my SPED Talk on data engineering in the synthetic image generation program to Android lifecycle. All right, perfect. So when you're making a machine learning model, you need t thousands and thousands of images for it be able to do anything, and you need to run it and train it all on a lot of epochs in order to do so. So you need um thousands of images, like I said. Um, and if you don't have the time to do it, well, that's a big problem. So I decided to go on the seed and grow synthetic data strategy. Um, I got me and my team to take. We didn't take many photos at all. This is the beauty of this part. We took about like maybe I took like 100 photos of parts in my living room and living area, and I think like my teammates took like 50 each of theirs. And this was in order so when the model would be live, the model would be able to pick up on their like live like textures they have in their house and living area. Um, and we'll touch on more on that more in a second. So, um. The synthetic pipeline used high resolution photos, 4K by 3K. I used OpenCV to overlay those onto about 10,000 images. So those what ended up being it was about less than 500 images, background images, combined with the source cards, which was like about four in the training was like four source cards. Um, in combination with using geometric augmentation. So, the card's rotated, the card maybe is facing like the depth's like a little off because of the surface area. So, like it's tilted an angle, and that's all normal in real life. So the model needs to be able to pick that up. It needs to be able to be accurate. No one wants to use an application where they can't where it doesn't work. So the application needs work. So in our case, if the application can't pick up where your card is, can't detect it, so then your application is broken. And so if your application is broken, no one's going to want to use your app. So anyway, so the model had to account for this. And so by using geometric augmentation, this is how we got it to work. Also, different times of day, photometric variation. So I used OpenCV to also, besides the time of day, so dimming of the lights, and um, we also used it to simulate quality of cameras. So a lower resolution camera to a higher resolution camera. And you can clearly see this here on the right hand top left photo of the same table. The left hand side looks of higher quality than the right hand side, albeit lighting variations, but it is clearly seen that the left-hand side has a more denser pixel population than the right-hand side does. So there we go. So we're letting the model pick up on many different nuances here. And so going on and moving forward, the training in the model architectures, I used GLOVA for real-time edge detection. Offloading a lot of this compute power to the user is really the way to go because not when you're not at Microsoft and you don't have a million computers, you do kind of have a million computers depending on how many users you have. You should really need to be using real-time inference edge detection, edge as in the user's phone, to do that compute for you. So, and that's going to rely on your model being very accurate. So you're going to have a finely tuned model. That way your model can just use your user's resources in order to do that detection. So, I designed it to train on 640 by 640, but it was designed on high resolution data. It was built using PyTorch, exported to a TF-Lite file that was able to be utilized in our Android application. I quantized it. I reduced the model from 32-bit floating points to 8-bit integers, speeding up the process by quite a bit. Um, so the Android sensor pipeline, at our core, because I was using an augmented reality application. This was another learning curve. Outputs to the YUV format and had to be converted to a bitmap, and I used render strip to do hardware acceleration. And the biggest learning curve here, and it was a big one, it was Kotlin's Kotlin's um native memory, which because Kotlin actually utilizes a library which is a C++ library. So long story short, Kotlin's like garbage collector cannot garbage collect the native memory being created by this C++ library. And so if it means you run out of memory and your application crashes, is what it means. And so, how to fix that and how to account for that, and we did, and it worked. And that was the long story short about it. So make sure you know what you're doing. Track by buffers. Card detector class. So a lot of scaling and normalization, um, because of inference via the TF-Lite interpreter and the NMS filtering that was used in order to, um, in case, so the card's going to be detected, every 15 frames per second. We only want one card version to be detected at a time. So if the same card, because the camera is moving, maybe the person has a shaking hand. We only want the camera to ever be um detecting one card. Imagine you move the camera and it detects now seven of the same cards in the same sector, and that's because you just moved your hand a little bit, and so it was shaky. And now, so you gotta use some post processing on that. I utilized a lookup table in Kotlin in order to quickly rename classes. Um, so yeah, so it makes renaming a breeze for monsters or whatever it is you're um detecting. So that's my SPED talk. Um, awesome. I was really glad to bring that to you guys. Have a great day.